The problem that we're given is heat transfer in a two-dimensional slab. So our two dimensions are going to be x and z. And the heat transfer is happening in this slab. And we're given that 3 of the boundary conditions are at a temperature we'll call T1. So in blue we have T1. And those are all 3 sides. And again, this is something that is told to us in the problem statement. We're not just pulling this out of thin air. The last boundary is going to be at temperature T2. And then, of course, the top and the bottom of this slab are both insulated so that we can neglect heat transfer here at this bottom interface, and again at the top interface. So there's no heat transfer at these edges. And this is simply the statement of the problem. We have to be given this information in order to set the problem up correctly. And at this point, it's pretty straightforward to write our boundary conditions in terms of the temperatures that we're given. So when x is equal to 0, we're looking over here, x equals 0. And so we're looking at a direction that's actually orthogonal to the x-axis. So the temperature when x equals 0 is looking at all values of z. And that is just this side. That's the side we're looking at. And so the temperature there is T1. And now we can do the same for this side. And in this case, what we're looking at is a location where z equals 0, but any value of x is appropriate. So any value of x, but z equals 0, and that's again T1. We do the same for this side. Here you can have any value of z, but x is going to equal the length scale that's characteristic to this problem, L. And finally, we have that last boundary condition that applies to this back wall, which has a different temperature from the others. And so at that position, you can have any value of x, but z is going to equal L, the length scale. And at that position, the temperature is T2. Now we need to set the governing equation for the problem that we've just set up. And so one way of doing that is using a differential shell balance. So that's what I'm going to show here, because that's something we didn't have time to do in class. Okay, so heat is flowing in the x and z directions. And so that tells us we're going to need something that has infinitesimal directions in x and z. So this is going to be delta x, and that's going to be delta z. And now the last dimension of this finite element, the shell, is going to be the same as the geometry of the problem, and that's not actually given to us. So that's a little bit messy there. We don't actually know what the height of the slab is, and we'll see that it doesn't matter, but we'll just call that h for the time being. And the important aspect here, again, is that the directions in which heat transferring are written as differential units, that is delta x and delta z. So we have our usual energy balance, in minus out plus net generation equals accumulation. Here we're still at steady state, so the accumulation is going to be 0. And you're not told that there's any net generation, and you have no reason to suspect it, so we'll neglect that. So we only have to consider our in and out terms. And this is where we need to consider the two directions. So there's going to be heat flowing into the x direction, and this will be at x, and this is at x plus delta x, where we'll have heat flowing out. And again, that heat is flowing in the x direction. We'll also have heat flowing in the z direction, and so we'll have heat flowing into this front panel and heat flowing out of the back panel. And that's at positions of z equal to 0 and, z equal to z and z equal to z plus delta z. So basically we've got two in terms and two out terms in our differential shell balance. So we'll consider this first term, which is flowing into this surface area. And the area there is just h delta z. But because the area is in the delta z direction, it means it's orthogonal to the x direction, and so it's actually corresponding to the x direction heat flow term. So there's the area times heat flow in the x direction at position x. And that's our in term for x. Our out term is again the same area, but this time corresponding to this panel. And it's, again, heat flow in the x direction at the position x plus delta x. We do the same for heat flow in the z direction, so we'll consider the front panel. And there we have h delta x times heat flow in the z direction at z minus the heat out the back panel. And so those are our in and out terms for the x direction. And again for the z direction. And all of this is equal to 0 because there's no accumulation in the system. Okay, so our next step is to rewrite this as something that we can turn into a differential form. So I'll scroll over to the next page. And what we have is we'll divide by delta x and delta z. And while we're at it, we might as well divide through by h as well. And so that's why the height of the slab doesn't come into play, because at all positions along that height, the temperature profile is going to be the same, because temperature isn't varying in the y direction. Okay, so now we'll just take the limit as both delta x and delta z go to 0. And the first term has no delta z dependence, so we can see pretty straightforward that we're just looking at something d dx, negative d dx, qx. And the second term, similarly, negative d dz qz equal to 0. And to turn this into a workable form, we're going to substitute Fourier's law. And it's important here to substitute the form of Fourier's law that applies to a particular geometry. We're working in the simplest geometry, the slab geometry. So in this case, qx equals negative k dt dx. And similarly, qz equals negative k dt dz. Where this really does start to get tricky is in the spherical and cylindrical coordinates when you're looking at dependences on phi or angle theta. But for the present, we're doing pretty well. And so if we assume that k is constant, and that it's also isotropic, we can pull that outside of the differential, and we have that the second derivative of each of these terms summed is 0. And it's no mistake, you can see that you can actually divide out by the thermal conductivity. And at steady state, the solution to the problem doesn't depend on the thermal conductivity of the material. And that may seem a little bit surprising, but if you think about it, it's basically just saying that it doesn't matter whether that slab is copper or plastic or cement. If you wait long enough, the temperature profile described by this equation will eventually result. And that's a subtlety of the Laplacian form of the heat equation, which is basically when you have no generation nor accumulation. If we were to have a generation term in here, things would get a little more complicated because you would have a K dependence. Okay, so this is the governing equation that we were looking for, and we've gotten to it from an energy balance, a shell balance, but we could have also just as well started with the governing heat equation for no generation, which is written as the Laplacian of T equals 0. And we just have to identify that in the Cartesian coordinate system, the Laplacian operates like this on a function. And in this case, our function is t. So we would have arrived very quickly at that governing differential equation, and it's just on us to notice that there are no variations in the y direction. And so we would have arrived at the exact same governing equation, whether we started with the vector form of it or whether we derived it through a shell balance. And so that's just a feature of these problems. Our next step is to non-dimensionalize the governing differential equation that we derived in the previous step. And so in non-dimensionalization, the aim is always to have parameters, and in this case our parameters are x, z, and t, and they're going to go to the non-dimensional versions, c, zeta, and theta. And we want these parameters to operate on the range of 0 to 1. And why we do that is so that these parameters, once the equation is solved, can be really easily applied to any problem that obeys the same governing equation and boundary conditions. And certainly that would be any similar heat transfer equation, but any problem that you can actually cleverly adjust the boundary conditions so that they collapse into the same situation as this one will be described by the solution that we're deriving right now. Okay, so to choose these non-dimensional parameters, it's pretty straightforward when there's a length scale involved, a clear length scale involved. And for C, that length scale is just L, the length of the slab. And so to non-dimensionalize, we usually divide the dimensional parameter by some characteristic value of that parameter. And since the characteristic value is L, it's very straightforward. The same applies for zeta. And the characteristic value here is the same as for the L direction because the slab is a square shape. So both the x and z dimensions are length L. It's when we get to non-dimensionalize the temperature that we have to think a little more carefully. And it's useful to reflect on the boundary conditions. We have 4 boundary conditions, and 3 of them describe a temperature, a Dirichlet boundary condition at temperature 1. And so it would be very useful to have the situation. We want theta to equal 0 when t equals t1. And so we're going to manipulate our definition of theta to achieve that. So theta is going to be some function of temperature over some characteristic temperature. And so that function of temperature we're going to choose is T minus T1, because whenever the temperature equals T1, the numerator of this expression will equal 0. That's halfway. That gets us to this part of our desired definition of theta. The other part is we want it to equal 1 at the other boundary, so that's when the temperature is T2. And so to achieve that, we choose T2 minus T1 to be the denominator. And that basically assures that theta is going to be somewhere in between 0 and 1. And that's exactly what we wanted for this non-dimensionalization. There's no singularly correct way to define these parameters, and in some instances there's multiple choices for how you can non-dimensionalize, and the best choice is usually the one that's most mathematically simple. Sometimes you don't know that in advance without having solved the problem, so these can be kind of an investment process. Okay, so in order to deploy these non-dimensional variables to non-dimensionalize this governing equation, we need to write the governing equation in terms of the non-dimensional parameters. And that's where the chain rule comes in. So we'll start by looking at the first term that we want to replace. And we break that apart into d dx dt dx. And then we further apply the chain rule to each of these parts. So d dx is equivalent to d dx to d dc dc dx. And so that is this term here is just this part here. Moving on, dt dx is the same as dt d theta dc dc dx. And again, this part here is equal to this part here. And the reason we expand it this way is so that we can then substitute in for each of these unknown quantities. Here's our unknown quantities. And then write this overall expression in terms of the unknown non-dimensional parameters. Okay, so to follow through on that, we need to implicitly differentiate each of these non-dimensional parameters. And for C, it's just 1 over L dx. For zeta, similarly, 1 over L dz. And for theta, it's just 1 over T2 minus T1 times dt. So we've just implicitly differentiated our non-dimensional parameters, and we can start substituting them into the expression on the right-hand side. So to do that, I'll just say I'm going to look at all of this only, and I've got ddc, and now dc dx, I have to look up here. That's where I get the solution for that. So dc dx is just 1 over L, so it's a constant. And that is my first term in the expression. Next, I need to look at dt d theta. So I come up over here, dt d theta, T2 minus T1, again, a constant. The next term, d theta dc, is one that I want in my expression, so I'll leave it. And then again, dc dx is just 1 over L. And this expression is just the second half of our original chain rule derivative. Okay, so the last thing to do is to simplify this. And we note that the constants can come outside of the differentials. So we have the constant t2 minus t1 over L squared. And then we're actually looking at a second derivative of theta with respect to c, because there's 2 differentials here. So we've non-dimensionalized the first half of the governing differential equation, and we'll go a little bit more quickly for the second half, which is with respect to z. This time we're differentiating with respect to zeta. Coming down to the next line. This is a constant, 1 over L. And again, we can simplify it by lumping the constants together. And so now we have an expression for the second half of the governing differential equation. So we combine the two parts of our governing differential equation. There's that governing differential equation, and here are the equivalent non-dimensionalized terms that we've just solved for. And what you can see is that those constants cancel out. So our governing differential equation is just d squared theta, dc squared, plus d squared theta, d zeta squared. And that's our non-dimensional governing differential equation. We've gotten this far, so our next step is to non-dimensionalize the boundary conditions. And here it's worth remembering that theta is going to be written as a function of c and zeta. So that's the form of how we write our boundary conditions for theta. And so it's pretty straightforward from our definitions of c, zeta, that when either x or z equals 0, c or zeta respectively are going to equal 0. So that's useful because we've got a couple of boundary conditions at 0. When x equals 0, that means c equals 0, but any value of zeta can be used. The caveat there is that we're assuming it's any value of zeta on the range 0 to 1. So we're not looking outside the boundaries of the problem, and that should be pretty obvious. But okay, so at x equals 0, we've chosen this boundary condition for theta such that at t1, theta equals 0. So that's one of our points where theta equals 0. We'll consider our other x position, x equals L. When x equals L, c equals 1. So at 1, at any value of zeta on the range 0 to 1, we have our second boundary condition at temperature 1, and temperature 1 equates to a theta of 0. We'll consider our boundary position for any c but zeta equal to 0, and that's the front face of the slab, this face here. So at that position, we also have t1, so theta collapses to 0. And finally, we consider the position where zeta equals 1 for any value of c. And that's the one boundary where the temperature is not T1, it's T2. And so if we come back to our definition of theta, at T2, we have that theta equals 1. And so those are our non-dimensionalized boundary conditions. Our next step is to solve the non-dimensionalized governing differential equation seen here. And to do this, we're going to use the technique of separation of variables. How do we choose that technique? Well, it only works actually for a very limited number of problems, and it works for the heat equation when there's no generation. It works for transient heat diffusion when there's no generation. It also works to solve the wave equation in one dimension. One of the things you kind of realize goes hand in hand with the separation of variables solution method is the fact that you have homogeneous boundary conditions, and that basically means that a lot of our boundary conditions here are equal to 0. Not all of them, but there's a lot of them, and so that might lead you to suggest a separation of variables solution. So the separation of variables technique assumes that the function we're trying to solve, theta, so it is a function of c and zeta, but we're assuming that it can be written as an independent function of c multiplied by an independent function of zeta. And at this point in time, we don't know what those functions, x and they're capital X, capital Z, are functions. We don't know what those functions are, but the technique takes us through solving to find a form of those functions. So if we make that assumption that a separation of variables solution will work, we need to then plug in the separation of variables form here into our governing differential equation. And this feels a lot like what we did when we were non-dimensionalizing the equation and we were plugging in those non-dimensional parameter formulations into the dimensioned governing equation. And it is quite similar. So for example, we need to determine what the second derivative of theta with respect to c is. And so that is d dc times d theta dc. So d dc. And here we're going to look up to our separation of variables formulation to determine what d theta dc is. So here, capital Z function is only depending on zeta. So in terms of c, there's no dependence. It's just a constant. But then x, capital X function, does depend on c. And so the dependence is d capital X dc. And if we differentiate again with respect to c, the same thing happens. Capital function zeta is a constant, and so what we end up with is d squared capital X dc squared. Okay, so that's one half of our governing differential equation, and we're going to do the same thing for the other half of our governing differential equation with respect to zeta. And in this case, when we look at that separation of variables formulation, we see that theta only depends on zeta through the function capital Z. So x is effectively a constant because it contains all of the c dependence. So our derivative is just x dz d zeta. And again, when we take the second derivative of that with respect to zeta, x is still a constant, capital function x. And we just get the second derivative of z with respect to zeta. I realize this seems a little bit silly, but now we've got the first term and the second term for our governing differential equation. So we'll plug that in. And we have, this is still our governing differential equation, but now we've assumed that a separation of variables solution exists. We'll call this separation of variables solution. And so this is the differential equation that we're going to be aiming to solve. It still has a second order term with respect to x and a second order term with respect to capital Z. But because it's a separation of variables formulation, we think that we can separate out those two dependencies. And it is actually quite straightforward to do this. Divide both sides by x and z. And so in this form, we've lumped all of the c dependence into this term and all of the zeta dependence into this term. To show why these two terms are interrelated, I'm actually just going to move one term to the other side of the equation. For me, that makes it appear more obvious. And it doesn't matter which side takes the negative. So when I look at the equation in this form, it says that any change in the parameter c on the left-hand side has to yield the exact same change in the differential on the right-hand side. And so unless these functions are exactly identical, which they're not, and we know that from the boundary conditions, the only way to achieve this is for these two sides of the equation to be equal to a constant. And the obvious constant we think of is 0, but if both sides of the equation are 0, there is no temperature dependence, and so we're not actually solving a differential equation. That's mathematically correct, but that doesn't go very far to giving you a temperature profile through the slab. So basically, our separation of variables technique has given us what is two differential equations that we can solve. And that's exactly what we were aiming to do, is to separate out the two equations so that we could more easily solve them. Because a second order linear homogeneous equation is much easier to solve than a second order nonlinear equation. Our next step is to solve the two separated equations using the techniques from the Sturm-Liouville problem. And so again, our equations are 1 over x, capital X, d squared x to c squared, and we said that was equal to a constant. And in this case, we're going to call the constant lambda squared. And the reason we choose a squared value is because 2 of the 3 solutions to the Sturm-Liouville equation then consider the square root of this constant. So it's convenient to square the constant to begin with so we don't end up carrying around square root symbols in our equation. However, because it's a constant, it is absolutely correct to choose any value. Or that is, any formulation of this value. And we remember that this equation, we decided the z half of the equation carries the negative sign when we separated the original governing differential equation. So here's our formulation of these equations, and the form of the Sturm-Liouville problem that we'll be looking at is, I'll write this in terms of y and x. Actually, technically, this is minus lambda squared y. So this is our Sturm-Liouville problem. And this is not the only form of it. This is a very specific form. And this specific form has three particular solutions depending on the sign of lambda squared. And for the time being, just accept that although it's a squared quantity, lambda squared can be either positive or negative. So if lambda squared is negative, that basically means this equation is written as right, because the quantity lambda squared is inherently negative, and the negative cancels with this, and actually, to be explicitly clear, I'll write this as the absolute value of lambda squared. And so in that case, the solution we have is a combination of sines and cosines. So that's our first case. We're going to need more room for various cases. So now if lambda squared is equal to 0, the solution we get is just linear. And this is not going to be the case for a two-dimensional heat transfer problem, so we can pretty much just forget about it at this point. And the other situation is if lambda squared is greater than 0. And in that case, to be clear, we'll use the absolute value of lambda squared. This term here is preceded by a negative sign, and so in that case, the solution to the equation is a combination of sinh and cosh, which could also be written as exponentials. So those are the three cases, and I'll put a dotted line between them. And so this case and this case are really the only ones that we're going to be using to solve our problems, because they're the only ones that give us a physically meaningful solution. Okay, so looking at the equation as written above, just for consistency with the course notes, what I'm going to do is this constant lambda squared, I'm going to call it negative lambda squared. It doesn't matter because it's a constant and we can choose it to be whatever we like for the purposes of solving the problem. So that means my first equation, which actually, to be clear, this is now, it's no longer a partial differential equation. It's a an ordinary differential equation. And so the reason I chose this term here, lambda squared, to be negative lambda squared is because I wanted to have a positive lambda squared over here. And I'm actually going to say that in this case, my lambda squared, I'm taking the absolute value of it, just to avoid this like slight confusion with the Sturm-Liouville problem statement, where the negative here is a part of the statement of the Sturm-Liouville equation, but then if lambda squared here in the first case is negative, then this quantity is inherently negative and the negatives cancel. That gets a little bit confusing, so here I'm just going to specify that my lambda squared value is positive and real valued. Okay, so this equation, as written, corresponds exactly to the first case. Oops, we've lost some text here. So this corresponds to the first case. In the solution, we can just write it. As a sum of sines and cosines. Similarly, okay, so that was probably the easiest differential equation to solve, right? Oops, that term doesn't go there. I've already multiplied through by x. Let me take care in writing this. Similarly, if we rewrite our expression in terms of z and z, oops, not c, and we'll use this absolute value of lambda squared. And in this case, we're looking at case 3 of the Sturm-Liouville problem. And so the solution that applies is this combination of sinh and cosh. And so we can just write that. And we'll use different constants of integration to be clear. And so these two equations together represent our solution to the Sturm-Liouville problem in its separation of variables form. There's still a lot of work to do, but we have solved the problem. At this point, we're going to take a little digression on the sign of lambda squared, and this is a for your information section. It will not be assessed. In the previous case, we chose lambda squared less than 0, and we know going forward that lambda is going to end up equaling some index n or m times pi, and that clearly corresponds to a positive real valued number. So what's going on? Okay, for lambda squared to be less than 0, lambda has to be an imaginary number, right? So we'll say that lambda is a plus ib. Now when we write lambda squared, it's a little bit of a misnomer because it's not actually lambda squared, it's lambda times its complex conjugate. And so if we were using wave notation, we would be writing like lambda, lambda star, which basically means here's our lambda and here's its complex conjugate. And so the magnitude of that, well, it depends on the relative values of a and b, right? Because if a squared is greater than b squared, then lambda squared is positive. But if a squared is less than b squared, then lambda squared is negative. So that's how we can make sense of a negative lambda, but it still doesn't explain why we're going to end up with a positive real valued lambda. And the fact is that our positive real valued lambda is actually the magnitude of lambda and not the true value. So if you remember, we often look at complex numbers on the complex number plane. And so this point here would be our lambda, and then lambda's complex conjugate is negative b. And so what you see is that the magnitude of lambda is the same for both of these cases, even though the imaginary part flips sign. So actually, when we say that lambda is positive and real valued, what we're saying is that the absolute value of lambda is positive and real valued. So that's just a quick explanation. Our next step in solving these two equations is to apply the boundary conditions. And here we have the boundary conditions in their non-dimensional form. And we need to further transform some of these into their separation of variables form, if you will. And this comes from the fact that we decided to choose a separation of variables solution where theta is a function of x of c and capital Z of zeta. So given that form we've chosen, we can say that this value of theta is x of 0, z of zeta. And if we do that, we have two options. Either x can be equal to 0, x of 0, or zeta, z of zeta can be equal to 0. So if we choose that z of zeta equals to 0, it means that we lose the entire zeta dependence of our solution, so we're not going to do that. So the logical choice here is to choose that x of 0 equals 0, because that only requires the function x to be 0 at this particular point, c equal to 0. So we'll do the same for these other three homogeneous boundary conditions, or the other two homogeneous boundary conditions. Again, we've got the same situation where either x or z has to be 0, and we're going to choose that x of 1 equals 0 because we don't want to lose our zeta dependence in the solution. And again, this time we're looking at one of our z boundary conditions, and we don't want to lose our solution dependence on the parameter c, so we'll choose that z of 0 equals to 0, because that only confines the dependence of the function z to one point where zeta equals 0. For this last boundary condition, we're just going to ignore it for right now because it's not going to be relevant. It's not homogeneous, and so it's not going to help us with our solution in this step. Okay, so we've rewritten our boundary conditions in terms of the functions x and z. Now we need to apply those to our solutions. So we have two solutions at this point. We have that x equals sine of lambda c plus a cosine term. And if we start by applying our first boundary condition up here, and we choose, there's only two x conditions, right? These conditions are both related to x of c. So we're going to use these to solve for x. Which one to choose first? The one with the most zeros. So when we apply the first boundary condition, this term is 0. And so we find that for this to be true, the constant of integration b has to be equal to 0. And so if we plug that into our expression for x, we've just simplified it. Okay, so now we can apply our second boundary condition, x of 1 equals 0. And the trivial solution is that a equals 0. This is not a good solution because it would mean we lose all of our c dependence for temperature, and temperature clearly depends on the x position. So we don't want to use the trivial solution. Instead, we'll use this boundary condition to solve for lambda. And so, just to write this more clearly, a sine of lambda equals 0. And so this gives us an infinite number of solutions for lambda. Lambda equals 0, pi, 2 pi, 3 pi, so on. And we'll take a little bit of care here in evaluating this first value of lambda 0, because if we come back to the Sturm-Liouville solutions, if lambda squared equals 0, that means that lambda equals 0, and we get a linear solution, and that's not physically correct. So we don't want to use this value of lambda. We're just going to let lambda equal some index times pi, and that index is going to start at 1 and go on up through the integers to infinity. So at this point we can rewrite the x part of our function in terms of c, and we can start thinking about the other half of our governing differential equation, the expression for z. And z, we said, was equal to a sinh and a cosh solution. And we do know what lambda is, so I could just substitute in for lambda, and I will do that in a moment. We'll come back and we'll look at our third boundary condition. So at zeta equal to 0, z equals 0. And this is really why the non-dimensionalization helped us so much, because it let us make these homogeneous boundary conditions. Sinches and coshes are quite similar to their sine and cosine namesakes, in as much as the sinh of 0 goes to 0 and the cosh of 0 goes to 1. And from this, we see that the constant of integration e has to equal 0. And so just to finish this line up, that means our function z reduces to a simple sinh. And at this point, the logical thing to do is to apply the last boundary condition, but we're not going to do that quite yet. What we're going to actually do is to combine the two solutions, and the reason you don't want to apply the last boundary condition just to the z equation is because then you've solved the two differential equations independently of one another, and so it doesn't guarantee that when you recombine x and z to make theta, that you'll get a solution to the total value of theta. So before we finish solving, we want to recombine our two solutions, again, according to the separation of variables solution that we've chosen. And here we have the c dependence multiplied by the zeta dependence, and here I'll substitute in for lambda since we know that lambda is n pi. And we see that there's nothing particularly unique about AD, so we'll define a new constant parameter called f, which is just going to be the product of A and D. And that helps us more clearly see that our solution is a function of c, zeta, and just one constant of integration. And that's the last thing that we need to solve for. And to do that, we will move on to orthogonality and superposition. To solve for our last constant of integration, fn, we're going to have to use superposition because we've actually got an infinite number of constants of integration to solve for. For example, if we consider the solution when n equals 1, we'll call it theta 1. We have theta 1 equals f1, our first constant of integration, times pi c, because n equals 1, times the sinh of pi zeta, zeta, because n equals 1. Likewise, we have a solution for n equals 2. We'll call that theta 2. That's f2 sine 2 pi c, sinh of 2 pi zeta, and so on to infinity. So we need a way of solving for an infinite number of constants of integration. And so you can kind of see that what we actually need is a formula, a mathematical expression that describes fn. And so to do that, we'll start by applying our last boundary condition, and then we'll see how superposition helps us. Actually, we'll apply superposition before our last boundary condition. Rather than dealing with an infinite number of solutions, we have to recognize that the temperature profile as a function of x and z in our original slab, and I'm just going to draw the cross section here, x and z, is real valued, and at any particular position, there is only one temperature that describes that position. That's the temperature of x, z at that point. Whereas the solution we have here suggests that you can pick any value of n between 1 and infinity and calculate a different solution. And that's not physically meaningful. So the true physically meaningful solution to this infinite set of equations is the sum of all of them. And mathematically, that's correct and rigorous because the solution to any particular differential equation in linear combination with any other solution is also a solution. So you can combine linearly any number of solutions to this differential equation and get another solution. It turns out that physically, the first people who solved this problem had to test it, but they found that to get the physically meaningful solution, you have to sum all the solutions. And so that's all we're doing here, is summing all the solutions from n equals 1 to infinity as an integer. And so that is the application of superposition. And the summation can be a little bit off-putting, but remember that the summation means that at the end of infinity additions, you just get a single scalar value. Whereas the solution we were looking at up here, that was actually an infinite number of solutions. Whereas this is just one solution. It's a complicated solution to calculate, but it's just one solution, and so this is physically meaningful. Always a good thing for engineering. Okay, here's when we'll apply our last boundary condition. And this stated that the temperature for all values of C and at the back of the slab, where zeta equals 1, was equal to 1. It looks like a pretty simple thing. When we apply that, theta equals 1, which is the summation 1 to infinity of this constant of integration. The condition is on zeta, so it doesn't affect C at all, but it does affect the argument of the sinh term, where we plug in 1 for zeta. So that's having applied our fourth boundary condition. The problem is we're trying to find a mathematical expression for f subscript n, and we have an infinite number of terms to consider in order to make that computation. And so because this series doesn't converge upon a particular mathematical expression as n goes to infinity, it means that we need to apply something outside of what we're thinking about now in order to figure out what that expression for fn could be. And this is where we invoke orthogonality. And if we were to solve lots and lots of these equations, it would become more familiar. We would recognize sort of this sign that triggers you to think of orthogonality. For the time being, just take it as a given part and remember how to use this, but I don't expect you to understand all the situations in which you should apply it, just this particular situation. So orthogonality is a unique principle of functions, and in this case we'll consider sine functions, which are orthogonal. And it means that for any two functions with very similar arguments, the only difference is the index m is, in this case, not necessarily equal to the index n. It means that the integral over a period is given by the Kronecker delta. And that's basically telling us that if m is equal to n, the integral is unity, and if m is not equal to n, then that integral is evaluated as 0. And in the tutorial, you can work with the orthogonality of the sine series, and mechanistically you can start to understand why that happens. And it is orthogonality is a characteristic of many functions that we use in physical systems like harmonics, and it is an actual useful property that enables us to analytically solve for solutions. Okay, so that's the definition of orthogonality. Definition. And now we're going to see how we can use this to solve the constant of integration remaining in our non-dimensional temperature profile. So we're just going to multiply both sides of the equation by sine m pi c dc. And you're allowed to multiply both sides of an equation by the same thing and expect the equality to hold. And so if we multiply the left-hand side, which is unity, we just get sine m pi c dc. And then if we multiply the right-hand side, it doesn't really matter because the summation index is n, and we're multiplying by m. So we could actually multiply outside the sum, but we're going to put it on the inside of the sum just for visual clarity here. And we've still got our sinh of a constant. And we're also multiplying by a DC. So at this point, we have just multiplied both sides of the equation by an expression. It is also perfectly acceptable for us to integrate both sides of the equation and expect the equality to hold. So we'll integrate both sides from 0 to 1. And this is not an arbitrary choice, because what it enables us to do on the right-hand side here, the summation and the integration at this point are relatively interchangeable. We have to make sure that all the terms containing psi are inside the integral, because the integral is with respect to c. And we have to make sure that all the terms containing n are inside the summation. So n goes with the summation, and c goes with the integral. In this case, we've put all of the terms inside both the integral and the summation, so we're doing just fine, not a problem. We could rearrange this to write the summation on the outside and the integral on the inside, and we'll just have a look at that because it makes it a little bit more clear. What we're doing, this is still the right-hand side. Maybe to make this even more clear, I'm gonna take the sinh term outside of the integral for the time being, and I can do that because the sinh term does not have a dependence on the parameter c. But I cannot take the sinh term out of the summation because it does have an n dependence. And so at this point, I'm not really solving anything. I'm just rewriting the equation, the right-hand side of the equation, so that the orthogonality pops out a little more clearly. I guess what I should also do to be absolutely precise is to multiply both sides of the equation by a factor of 2. So I'll come back up here and multiply this by 2. I'll multiply by 2 over here. So we've still got this 2, we've still got this 2. And this is the right-hand side of the equation. And actually I'm gonna move that 2 right before the integral so that it looks exactly like the definition of orthogonality down here. Okay, so let's just evaluate a couple of terms in this summation, right? So the summation n equals 1 to infinity of this argument. I'm not going to write out the whole argument. It's going to equal the sinh of n pi times, we'll start with n equal to 0. And let's say for this situation that m equals 3. So when n equals 0, n is not equal to m, and this integral here, n is not equal to m, so that integral is 0. So 0, and that's n equal to 1. Okay, now n equals 2. Well, n is still not equal to m if we assume that m is 3, so it's still 0. All of a sudden, we get to n equals m, and this integral is going to be the Kronecker delta. And so we'll just write the integral as it is for sine squared n pi c dc, because n equals m. Actually, this n, maybe I'll write it as an m for clarity. And that's our third term, n equals 3. And I've just chosen this quite arbitrarily, what n is, what n is. Okay, so we keep going, dot, dot, dot. Our next term, n equals 4, plus 0, plus 0. Every other term in this series is going to be 0. So the only time that one of these terms is non-zero is when n equals m. And when n equals m, what we get is sine squared m pi c. So that's basically why there's only one term in the whole of this series that has any value. And so the summation, we're still just looking at the right-hand side of the equation. The summation from 1 to infinity reduces to the sinh of n pi times the integral of sine squared m pi c dc. And on the left-hand side, sorry, there's a factor of 2. We've still got 2 integral 0 to 1 sine m pi c dc. And the factor of 2 ends up canceling out. That should be a limit of 1. Okay, so like the whole aim there, and I've definitely lost the coefficient fm along the way. Put that back in, because that is, after all, what we're solving for. This whole side times f. We'll change it to fm in the last line because m and n are equal. We can do the same with the argument of the sinh and change that n to be an m because m and n are now equal. So we've basically used orthogonality to change an infinite sum into one term, and that term is where n equals m. So now we can continue to solve this just by, well, normal integration. So on the left-hand side, the integral of sine is negative cosine. And you divide by the constant part of the argument and evaluate between 0 and 1. On the right-hand side, we've got that constant of integration we're solving for, the sinh of m pi. And inside of our integral, we're going to use the half-angle formula for sine squared, which is 1/2 1 minus cosine of 2 times the argument. And that just facilitates the solution via direct integration. Coming back to our left-hand side, we can evaluate the limits of integration. So we have the negative cosine of m pi minus the cosine of plus the cosine of 0 over m pi. Cosine of 0 is 1. And so we'll skip down one more line and we'll just write this as 1 minus the cosine of m pi over m pi. And we can simplify that a little more, or at least change the form, but we'll leave it for the time being. On the right-hand side, we carry over our constants of integration, or our constant of integration and our constant, and we evaluate this expression, the integral, which is the integral of cosine is the sine, and that's divided by the constant terms in the argument. And we're going to evaluate that integral from 0 to 1. And so if we come down and actually do that evaluation, still carrying our constants, we have 1 minus the sine of 2m pi for 2m pi minus 0 minus the sine of 0 over 2m pi. So both our expressions with sine are 0 valued. So our solution, we're pretty easily able to solve for fm at this point. So we'll bring over our 2. And we'll bring over our sinh. And that's equal to fm, which is our constant of integration. So the only difference here from the course notes is the term cosine m pi, which, so for m equal to 1, that's negative 1. For m equal to 2, it's positive 1. And so forth. It just switches between negative 1 and positive 1. And so we can rewrite that as negative 1 raised to the m. So we'll replace that in the expression. And again, that's not really necessary. I think it just sort of simplifies the expression a bit. So given this value for fm, we are finally able to write out the full solution for theta. And that is well, it comes from fm sine n pi c sinh n pi z. And now that we know what the value of fm is, substituting in, this is defined as an infinite sum. So just substituting in for fm. And I'm going to change those indices to m, because m and n are equal henceforth. And we have our full solution for theta, and again this is theta as a function of c and zeta. And if you wanted to write out the dimensioned solution, you could just substitute back in that theta equals t minus t1 over t2 minus t1. And likewise, you could substitute that psi equals x over L and zeta equals z over L. And then you would have the solution back in our original spatial coordinate system. But I think the non-dimensionalized form is slightly simpler. And the other advantage to the non-dimensionalized form here is that you can just easily apply it to any situation. So if we were looking at our block XL, XZ with length L, and we decided we wanted to consider a block with dimensions 2L, well, we would just basically for L insert 2L into this non-dimensional form numerically, but the solution would be exactly the same. For example, because it's non-dimensionalized 0 to 1, 50% of the way along the Z direction is going to have, at any particular point X, the same exact temperature as 50% along the slab if it's a shorter or a larger length. So that's really the power of non-dimensionalization.